Okay. Howdy, it's Haka says here, and we're over in Tonopah, Nevada, doing an experiment at the seismic mine. The reason we're out here is because there's some future experiments where we want to get a seismic receiving station that was abandoned by a university some years back. We want to do some tests to calibrate and measure to find out what type of output the seismometers actually create. And then knowing that information, we can build a proper interface circuit so we can attach a proper data logger and start turning these signals into direct live feed internet signals like they used to be a long time ago. So the first test that I was doing was to just try to look out the pinout on this to try to figure out what was hooked to what. The second test, right now, we're going to hook up a crude digital multimeter to try to get the coil resistance. And it looks like when we're probed on here, we're getting about 61 ohms of resistance on the coil. We could try panning around to a couple other points here, but I wasn't getting any other reading on other test points, so I think these two are the primary feed lines out. So 60.8, 60.9 ohms. It does seem to vary quite a bit, probably because the coil inductance changes it. So 60-ish ohms on that. Next we have a LCR meter. And in the same way, I want to try to test the inductance of this coil. Because as long as we have all the measurements, the better measurements we have, the better it's going to be to make an adapter to hook with this. So inductance, once we hook that up, we get approximately, yep, that's a big geophone. Is that millihenries? Let's recalibrate. So something's off because it's giving a reading of negative 720 milliohms. I'm wondering if it's because the frequency I'm using is too high for it to register. So if I change to 100 cycles, recalibrate. So now if I read it, we get, yeah, that's more reasonable. So LCR, we're getting a reading of 7.488 henries. That's a very, very large coil. 7.489, 7.488. And if I tap it, it changes, so I know this is attached to the geophone. So 7.5 henries. So those are the two tests that we have here. The final test is to try to hook it up to the oscilloscope and see what type of signals we get directly off of it. Is that a good angle?
Yeah, it looks pretty good.
Cool. Let me know if the light's in the way. So I already got this into the right range. We have the scope on a 1x probe, 200 millivolts per division. It's a lot of voltage. I wonder if there's interference from the inverter that we're using or something similar. But the noise is quite high. I don't know how to resolve that. I wonder if we ground one, if we had a better system ground. Oh, okay. I grounded the system.
Just onto the body of the transducer?
Correct. Apparently there's a part of the circuit that needed that. So now I bring it down and speed up 1 millisecond at 50 millivolts per division. So if this is correct and I tap it, we should get a nice, good,
I'm
yeah.
already seeing your
Look
voice.
at that, look at that warble.
Wow.
Go ahead, stomp your foot a little, watch what happens.
Yeah. Even just you speaking in front of that.
Yep. La. Well, it was happening when we were testing the previous time, is just the voice.
Yeah,
that's it.
You can see it.
Yeah, you
Right.
can see just as I'm talking, the my voice inside the inside the geophone. So as these experiments, 20 millivolts per division, and if we do a tap, let's see what kind of signals we get. So really light tap. Actually, so neutral noise is almost zero. That is actually talking is about let's see, 5 millivolts, 5 to 10 millivolts from just audio speaking. Very light taps on the ground. Seems to generate at least 40 millivolts. It looks like peak. About 40 millivolts peak on here. Tap goes off scale still, so I'll keep going higher. So 100 millivolts per division. That's nice and reasonable. So you can see just from tapping, a completely unpowered system is generating over a volt on the system just from the multiple Henry coil that it's coming from. So I think this should give us enough of the data that we need. I always want to take more data than I have to, but I think this should give it a good idea on earthquakes.
Right. And ultimately, there's 3 transducers, right?
Correct. So
So
there's 3 of these geophones. So whatever system that we have that amplifies these recorded signals and puts them online, it's going to have to be 3-channel. It's going to have to be 3 separate receivers that all collate into one.
they'd all be oriented in a XYZ axis sort of configuration, yeah?
Actually, you could see that now. There's the one that's in the back is oriented vertically, so that would be a Z or up-down axis. The one here, I don't know if this is north-south or if it's east-west, but let's just say that's north, north-south. And then if you pan around to the other side here, on the other end of the room, there's another one that is panned 90 degrees to the one that you were just seeing. So X, Y, and Z.
All right.
Very light taps, 10 millivolts or so. So we know whatever we're going to do, because absolute seismic signals are going to be lower than this. We're going to need an amplifier that can read a signal well below 1 millivolt. So we're probably going to be working in the microvolt range. But the signals are very large. We can see it goes over a volt. So there's going to have to be an interesting, either an automatic gain control or some type of a very high dynamic range. So it doesn't blow through the top of the system whenever there's an actual earthquake nearby. But it'll be interesting. Seismic station, not only just to have an old station return to service back online, for the long term, but also because having our own seismic system is going to give us a good secondary sample set of data to compare against the telluric receiving system that's just a short distance from here. So anyway, Haka says, hope you enjoyed the video. EPD Laboratories experiment, what is it, Thursday the June something. But anyway, hope you enjoyed.